Keep on going. So I have a background in astrophysics. I did my doctorate in gravitational waves with the LIGO collaboration. I did leave a year before they won their Nobel Prize, so I can't really count myself as that. I did have a bio written for me once that really made me sound like a Nobel Prize winner. I didn't super hate that, but I did have to explain to people that that was the case. But after I left academia and research, I started doing science education, and I used to work in science museums doing live planetarium shows like this and doing Q&A in the space section. So when I posted this on Twitter, I had a few people ask questions. One I thought was a direct question to me, not a response to my tweet, and so I actually answered it, not realizing it's been a week. But the first question that I got was asking what the initial coordinates of the Big Bang are. Like, where's 000 in our universe? So the Big Bang, is the beginning of our universe. Our universe has a start. Our universe is everything that we know. And it started approximately 14 billion years ago. And we can study something called the cosmic microwave background, which is like this residual heat that exists in our universe that's left over from that. And it's approximately 3 degrees Kelvin. So just a little bit above absolute zero is just this residual heat in our universe because of leftover from the Big Bang. But where is the origin of it? And this is hard to wrap our minds around. And this is why a lot of astronomers live in a state of existential crisis, which is fine. But the best analogy I can think of is to think of our universe like raisin bread, right? So when we talk about our universe expanding and we see everything red shifting, which means everything around us is moving away from us, what does that actually mean? So yes, a bunch of DragonCon science track people here. Awesome. What does that actually mean? And how do you picture that? And if we see everything moving away from us, are we the center of the universe or not? And we like to think we are, but we're not. And so where is the center? Where did the Big Bang start? Totally valid question. The best analogy to think of this is to think of it like raisin bread. That's kind of how I imagine it. If you imagine raisin bread or your other baking comfort food of choice, I literally have banana bread sitting on the counter cooling right now. But if you think of that, the raisins, as the bread expands and as it bakes, all of the raisins are moving apart from each other. So if you were at the focal point of any raisin, you would see them all moving away from you. And if you were on another one, they would all be moving away from you. That's one way to think about that expansion of our universe, of everything moving away from everything else. And again, going back to the cosmic microwave background, that's that residual heat as that bread cools down, right? The temperature is going to cool off. To just keep pulling on this thread in this analogy, you can also think of the crust of the bread as the origin of the Big Bang. If you think of it more than, if we think of the Big Bang start and then expand, that's our origin. It's not so much here. It's expanding, and it's expanding in infinite directions. And this is where the analogies start to break down and where we start to get headaches real fast, which is okay. But I hope that kind of helps to not think of our universe as like one central point, but more the Big Bang is like that bubble that surrounds us as the universe continues to expand. We don't know what our universe is shaped like. This is a field called cosmology. And what they do is they try to figure out what our universe is actually shaped as. And a closed universe would mean that it is literally a bubble, that it does close. And if you were able to travel long enough in one direction, you would circle this entire sphere and come back. And it will eventually slow down and then crunch. That's the big crunch, is the end of the universe if it's closed. If it's flat, it's just going to keep on accelerating at the same rate and keep expanding. Yes, in infinite directions. And this is the hard thing to wrap our minds around. So we can't say this for sure, but this is what cosmology is trying to figure out. All we know in our universe is what has had enough time to travel to us, right? That 14 billion light years. If you imagine it all going off in different directions, we're only going to be able to like backtrace in the light cone of where we're going. And I don't want to get too in the weeds because we do have a lot of stuff I want to talk about. Well, we can come back to this. Ask more questions. Please feel free. I love talking about this. Just to finish out that cosmology talk, there's closed, there's flat, and then there's open. And like geometrically, if we get really in the math world, it's kind of saddle shaped, and it just means it's going to continue accelerating as it expands. So it's going to get faster and faster and faster, and it will fall apart in the big rip. Which is fun to think about. But astronomers are still trying to figure this out. So if you look at like WMAP, other telescopes and satellites that study the shape of our universe, that's what they're looking for. They're trying to see if it's flat. And so far as we know, it's flat. But again, are we just an ant on a giant beach ball that thinks its world is flat? So I hope that helps. So another question was, how do you orient yourself in space? Where is north, south, east, west? Up, down, left, right, all directions. That's a really good question. And we, for simplicity on Earth, keep it pretty centric. A lot of the way that we talk about space is, thankfully, because of angular momentum. And if you've taken Physics 101, right-hand rule, anyone remember that? The right-hand rule? If you don't remember this, it's basically talking about rotation and curl. And thank you. And what's happening is if you can say that, like, for example, a cylinder or a solar system, all of the planets are orbiting in one direction, you move your hand in that direction, and then where your thumb is facing is up. If you go the other way, then your thumb is facing, that would be down. And so that's how we kind of orient ourselves more in terms of rotation than trying to think of north, south, east, and west. Once you have that rotation coordinate fixed, then you work in that. So it's more like, again, I don't know if anyone remembers this. We're going to call back some math and science. If you didn't learn this, that's okay. But radial coordinates as opposed to X, Y, and Z coordinates. So here on Earth, we use mostly X, Y, and Z. Go this far east, this far north, which is opposite for what you're seeing on the camera, but you get it. Radial coordinates are more thinking of a center point, a distance from that center point, and then the angle that you're going in that direction. And that's more thinking of like galaxy coordinates, stuff like that. So that's how we orient ourselves. Again, I mean, Star Trek did this, right? They put sector 000, sector 1, where Starfleet was. And so, that's one way to do it too. Okay, so some space news that I wanted to talk about. The first thing is that there were a lot of questions if the current world situation, which I don't want to dwell on too much because it's on fire and we're using this to escape right now. The rover Perseverance, if you remember Mars rover 2020, that was in the news a lot. That's the next kind of big rover. So Curiosity was the most recent one that we're all attached to because Wally lives on Mars now. The next rover is going to be the Mars 2020, and it just went through a naming competition. So it's now called Mars rover Perseverance. So Perseverance is still on track to be launched in July. That's the current update. A lot of people were asking about that, and apparently it is still on track to be launched by then. The other cool, I want to pick like one big space news thing that I'm going to geek about, one, thing that hit the headlines that I can super nerd about and explain the science behind it. And the reason I'm doing this is because when people find out in casual settings that I'm an astrophysicist, it usually ends up being like, so I saw an article that I thought was really cool, but I don't understand any of it. And can you explain it? And so I'm going to pick my favorite cool article and explain it. And hopefully you enjoy that. But recently a study just came out about the Supernova 1987A. In astronomy, this is SN 1987A. This was a supernova, a big bright flash of light that we witnessed here on Earth in 1987. And we've been studying it for a long time. The reason is it was really bright. It was really recent. We had some good data, and it was close-ish. So we have located to a place we call the Large Magellanic Cloud. So we have, and I'm doing my cosmological address. Yeah, same here. Cosmological address. We have our star system, our little planetary system, which we're going to get to in a second. Then you have our star system is one of many, many billions of stars, hundreds of billions of stars in our Milky Way galaxy. So we have our star system, our Milky Way galaxy, and then our galaxy is one galaxy in a cluster, a local group of galaxies. And then those galaxies, the galaxy cluster is part of a lot of galaxy clusters in our universe. So our universe is everything, shrink it down, You get to galaxy clusters, you get to galaxies, then you get to star systems, then planets, and then your street and your city and state and all those things. So if you're going to write to an alien, you have to put all that information in there. So this supernova 1987A, it took place in one of the other galaxies in our galaxy cluster. So not the Milky Way, but the Milky Way, which is a big flat spiral galaxy, has like two little companion galaxies. They call the Large Magellanic Cloud and the Small Magellanic Cloud. And this one was in the Large Magellanic Cloud. So this little cloud, it's not spiral shaped, it's what we call an elliptical galaxy that hovers around the Milky Way galaxy. So it's still a cluster of stars, it's just not a spiral. And that's where this supernova took place. The reason this supernova is weird is a supernova is when a star dies, when a massive star dies, all the outside layers collapse down and then it contracts and then all the outside layers keep falling and they bounce off once physics says no, they bounce off and go off, they get ejected. And you see this huge flash of light and it's bright for a long time. And so this only happens with supermassive stars. Our star, our sun, will not supernova. It will expand. Once it runs out of hydrogen, it's going to start expanding, and then it's going to turn red. And this is in billions of years. So kids, don't worry about it. It's going to be a long time in the future. I did super upset a lot of children the way I described it once. But it's going to keep expanding once it runs out of hydrogen into a red giant, and then once it runs out of fuel, the outer layers are going to fizzle off, and what's left behind is a white dwarf. Supermassive stars will go through their life, they will expand into red giants, then they will run out of fuel, then nothing's holding it up anymore, so it's all going to collapse down, and then, like I said, the outer layers are going to hit it, they're going to bounce off, and you're going to get this bright flash, which is a supernova. What's left behind is either a neutron star or a black hole. So the neutron star will be left over. And if it can't hold up against its own gravity, it's going to collapse further into a black hole. So that's kind of that supermassive star. So we observed a supernova in 1987. And the weird thing about it was it ejected nickel real fast, like hauled out of there. And none of the models that we've had for supernovas explained how that nickel could book it in the way that it did. Now, they've been studying it for over 30 years, trying to figure out what models this were. And this is why I love astronomy, because what happens is we are like in this constant state of theory and observation. We see something and then we try to figure out why it did what it did. We have a theory and then we try to wait for an observation to actually see it. Supernova are a really good example of trying to balance all of that. So this supernova, we saw something weird. Now we have to try to figure out the physics behind it to see if it's breaking any of our physics rules or if we're actually able to explain it. So like I said, this nickel ejection was super, super weird. They weren't quite sure what caused that supernova to behave the way it did. They call it an asymmetric supernova, which means it doesn't go off perfectly spherical. It's like bulges off in one direction and a little bit less in the other. And they've gone through all these models and computers have got better, so they're able to model more weirder stuff. And they realized that this is a supernova that was caused by a compact super blue giant. Right? So what the heck is a super blue compact giant? They realized super compact blue supergiants are formed by merging a red supergiant, so giant red, massive, hundreds times the size of our sun, with like a normal star. It merges, stuff goes weird, and you get this compact blue supergiant that won't live very long, can't sustain up against itself, and then when it died, that resulted in the 1987 supernova. And when they had that weird, messy model, that actually showed nickel going like getting shot out of there, that they think that nickel was in those layers because they had exactly like a companion star that swallowed the other, that you had this, it was likely, again, I just read this in the news. I'm geeking out about it. I wasn't part of the research, but likely the red supergiant absorbed the main sequence star. And when it absorbs that, then you have a lot of gravity going on. You have a lot of different components that are creating different elements because you have a lot of mass that are very dense and compact. And then when that supernovas, that all gets ejected out. All that weird stuff, it wasn't necessarily made just in this core. That we had this nickel that was formed that then when the star supernovaed, it went out. And this model matched. So that was the recent news, is that they realized what caused that to happen. And that might seem small and inconsequential, but I read that article and I was like, that's awesome. That's awesome. Because I didn't realize that that was the weird thing about 1987A, that it shot nickel out at like tens of thousands of kilometers a second, which is objectively cool. The other thing that this team, it's the Riken Astrophysical Big Bang Lab, have been the ones studying it. They published the paper. The other thing that they discovered is that they think that they've also found the leftover neutron star. So when I talked about the supernova, what's left behind is either a neutron star or a black hole. This is a neutron star that was left behind, and they were able to find it slightly offset from that explosion that happened. So, cool astronomy news of the week. That's what we'll call this segment. Okay, so there were 2 requests for planets that we want to talk about, and this is where we're going to transition now into my little planetarium getup. So hold on to your butts. We'll see if this works. All right. I think we've got this set up okay. So I can run our planetarium software here. Please let me know if you can't see this. If you can't see this, I don't have another option, but I can talk through it and we'll figure it out for next time. But this is at Griffith Observatory. I live in LA, but I didn't want to put my exact GPS coordinates into this. Yes, this is the Stellarium app. This app I started using when I was a science, when I was in grad school. When I started going to teach astronomy at schools, we would take a inflatable planetarium into the gym, inflate this big balloon and let all the kids crawl inside, which they love. And then this software actually has a capability to project on a mirrored projector, so it can actually be it can project onto a round surface. So it's really great for that. It's very easy to use. It's free. It's a little intimidating at first, but once you start poking around, it's not too bad. So we have, this is kind of not what the Griffith Observatory looks like now, because it's not out in the Midwest plains. But this is just our simulated ground. And what we can do is we can actually take away the atmosphere. So this is what it is right now. I'm on current time at the Griffith Observatory. And now we can see what's in the sky right now without the atmosphere. So I've removed the atmosphere, which means we can see the stars. And if that didn't make sense to you, that's okay. The reason the sky is blue is because our atmosphere scatters blue light from the sun. So the sunlight hits our atmosphere, it scatters blue light, and that's what makes the sky look blue and covers up the stars. I think that made sense. So now we can start to see what planets are in the sky right now. You can see our coordinates down here. So we're looking west. We have some cool stuff in the sky. But let's go to what it's going to sort of look like tonight. And we're going to talk about Venus. So I'm going to stay facing this direction. And we're going to set the time for a little bit later. I want to make sure Venus is still in the sky, but once the sun is set. All right. So here we are. This is about 8:20 tonight. Again, in LA. And if you want, I'm planning on doing this for an hour. So if we run out of questions, if you just want to see what the sky's going to look like where you are, we can do that at the end. But the sun has set. We're looking directly west. And we're going to talk about Venus real quick before we talk about the other stuff. Yeah, the dark sky with the sun there is super weird. So the reason I want to talk about Venus right now is because it's actually at a really interesting point. So for those of you amateur astronomers or astronomer wannabes or taking astronomy up now, Venus is actually at a really good point. And I want to thank Todd for bringing this up and pointing that out. Ask Todd anything here. So Venus is our closest planet to the star. I want to explain why it's cool now, and then we'll go into some science about Venus itself. But the reason it's interesting now is because it's at its greatest elongation. So it's the furthest east from the sun that it will normally get. So again, we talked a little bit about, the fact that the sun just set. But if you paid really close attention, it kind of moved through the sky like this. And so we're west now, but throughout the day, Venus is east of the sun. So if the sun was here, Venus would be up here. Back when we were looking at it earlier, Venus was east of the sun from our position. And it's the furthest east that it's going to get. It's going to start moving closer to the sun again. And the reason this is cool, and this is actually really easy astronomy that you can do yourself, is Venus actually has phases. Really, really cool to see. So let me see if I can, I don't know if I can pull that up right now. But what I mean by that is like the moon has phases, right? So right now, if you were to look up in the night sky, the moon would be at, I think, is it half? I don't know what the phase of the moon, I should know what the phase of the moon is right now. We're still learning how to do this. But the phase of the moon is at the very least, it's going to be bright on the side close to the sun. That's the easiest way to think about it. It's going to be dark on the other side. That's why we see the phases, because we're seeing the sunlight reflecting off of it. So the sun's sitting here, and then it's pointing to us. 10% waning. Awesome. All right, thank you. So that means it's a small thing, and then it's getting smaller, which makes sense. So it's moving in this direction, day by day by day, not throughout the night. Day to day, it's moving further here, which means it's going to start, the sun's going to basically start to be behind it. We're not going to see an eclipse because the alignment is going to be such that the moon and the sun are offset from each other, but we're not going to see any light reflecting off of it. We're just going to be seeing a shadow. So 10% waning. Thank you. So it's going to be a very, very tiny crescent. And then night to night, we're going to go and it's going to be a new moon, which again is when we just see the shadow. We don't see any reflected light. But Venus does a similar thing. Now, the fact that it's the furthest east means you're going to see the bright side on half of it. The other half is going to be dark. You can actually see this. Hey, thanks for using that. You can actually see this, and you can convince yourself you can see it with the naked eye. You can definitely see that it's not perfectly round. That's the cool thing about it. You can see that it's not perfectly round. If you have binoculars, you can actually see the phase of it. And obviously, if you have a telescope, you can see that too. But actually, half of it is lit up. I am going to hop real quick back over to this because I put it up in here, but I didn't put it up on the planetarium setup. But I do have this image. So these are notes that that again, Todd shared with me, and I remember from astronomy. These are Galileo's notes about observing Venus. So once he was able to observe Venus with his telescope, he made these drawings that he could see the phases of Venus. And this was sort of the first big indication that Venus orbited the sun. And you could only really get this effect if we were both orbiting the sun. So that was sort of another explanation for why that is the way it is, which is pretty cool. But Venus itself is pretty awesome. Obviously, it's the second, I don't want to say obviously, because some of you may not have taken astronomy, so I'm sorry if I'm saying something that's meant to be condescending. It's not. Feel free to ask any questions at all. There's no dumb questions here. I'm very happy to have you here. So Venus is the second planet from the sun. It is about the same size as Earth, so we always kind of called it the sister planet, because it's very, very bright in the sky. If you don't count the moon, it's the brightest object in the sky. We can see it during daylight. So even if the sun is there, we can see Venus because it's reflecting. It's very, very reflective. It reflects sunlight, and we can see it because it hangs close to the sun. Right now, this would be our evening star, because right before the sun sets, that's the only star you can see is Venus. Star you can see. And that's why it was studied so much. So Venus is very reflective because it has this incredibly reflective atmosphere. And astronomers, when they were studying it, realized that it was close to us. They realized that it had a comparable mass and size to Earth. And so for a while, that was like, oh, and it had an atmosphere. So it was like, oh, this could be the place that we want to visit first. You know, honestly, without knowing anything, that might be a place where we try to settle, right? Put yourself back in the mind, like, 100 years ago or something, that might be the case. And so they went to go study Venus, and when they tried to launch a probe in to take pictures of the surface, because we couldn't see through the atmosphere, the probe is like falling through, and then it just goes and collapsed in on itself before it even made it through the atmosphere, which is hilarious and awesome and sad for the probe, but cool for us. And this is because the atmospheric pressure on Venus is 92 times that of Earth. So if you take our atmospheric pressure, that's the column of air that sits above our head, that where yeah, right, exactly. The column is right up ahead of us, and that weight is on us. Imagine that column got 92 times heavier. And one thing that I really like is actually, if you were to add up all of the atmosphere above our head and compact it all down, it's about the weight of a car. But we've evolved to be used to that, so it's no problem for us. But that's one atmospheric pressure. Venus is 92 times that, so that's a lot. And this probe collapsed before it even got to the surface, so that's a problem. Not ideal for us. But still interesting to study. So we kind of ruled out, okay, we can't really walk on the surface, and the atmosphere is a ton of carbon dioxide, a lot of sulfuric oxide, I think, which makes it smell terrible and kind of poisonous. As we've studied Venus, we've learned a lot of things about it. Now, some kids, and I remember doing this at the museum, sometimes we would kick these off with just saying, all right, what's your favorite planet? What do you want to go to? Because we had these prompts, I didn't do that this time. But Venus is, one kid was like, Venus. I was like, oh, cool. Don't get that one a lot. Why? He's like, because you can have your birthday twice a year. Great fact. So for those of you who don't know this, Venus rotates in the opposite direction of Earth. So again, I'll come back to that, but we talk about the rotation of the solar system. All of the planets go around the sun they orbit in the same direction. Most of them also rotate. So the whole solar system's doing this. The planets are also rotating themselves in that same direction. But Venus is actually going opposite. It's still going around the sun the same way, but itself is rotating slower. And indeed, so it takes, I wrote this down. I do not have this stuff memorized. It's okay to not have things memorized. 1 year on Venus is 225 Earth days. So 225 Earth days. But its rotation time, its own little orbit, so like Earth, our day is 24 hours. Its day is 243 Earth days. So a 225-day year and a 243 day rotation. Day. And so this kid was fairly right. That was a great way to absorb that information. We've been trying to figure that, sols, I guess, is a good way of phrasing it. That's sort of the way we talk about Earth days, is one sol. That's how we refer to them on Mars. So how many sols, how many sols is that planet's day? So a Venus sol is 243 Earth days. I think that makes sense. But the cool thing about this is we've been trying to figure out why that's the case. Why is Venus rotating so incredibly slowly, right? And in the opposite direction. So the other planet that rotates not with the orbit of the sun is Uranus, because Uranus is actually tipped on its side. So the North Pole faces the sun. And like Uranus, we also think maybe in the early formation of the solar system, something hit these planets that knocked them off their course. because the solar system all formed out of one big ball of dust and gas, it started to coalesce, and we started to get all of these, they all started rotating in the same direction, because you had this whole big ball of dust and gas all rotating and then eventually flattening out and sort of clumping out, and you got the sun in the middle, and then you got all these planets going around, and they're all rotating in the same direction. And the ones that are backwards, the best models we can think of for this is that they got hit with something that screwed up that rotation. So that's what we think happened to Venus, which is pretty sweet. It is the hottest planet in our solar system. So most people think that because Mercury is the closest to the sun, that it's the hottest. But because of the greenhouse effect, Venus is the hottest. It's up to 900 degrees Fahrenheit, about 450 degrees Celsius on the surface. So in addition to the atmospheric pressure, temperature is not ideal. However, there are legitimate, and I love that these are legitimate, not just my headcanon, explanations for how we could possibly visit Venus. And one of those is we can build a cloud city on Venus. Pause for effect, because that's amazing. That we could basically build a cloud city at one atmospheric pressure. So as you're going down, it's getting denser and denser and denser. Exactly. It's getting denser and denser. And then you reach a point where you are, the column of atmosphere above you is one atmospheric pressure, and you just chill there. Now, you still wouldn't be able to breathe it just because of the composition. But this is legitimately being considered as a way to build a civilization on another planet. The discussion of should versus could is kind of comes into play there, but it's just objectively awesome. So we're happy to talk about that. So that's Venus. We have taken pictures on the surface of Venus. We have now understanding the composition and the pressure and how long. We've put landers on the surface. That have been able to take pictures so we can image it, and it basically looks like Mars with a big yellow atmosphere. No need to worry about global warming because Venus already went through that. A lot of the people studying Venus are trying to figure out if it did resemble Earth in the past at some point. Its surface, oh God, I do not trust these numbers because don't have them written down. But I know it's 102 to 300. I think it's 100. The surface, the crust of the Earth is 100 million years old. And the crust on Venus, because we've taken pictures, and we've done more than take pictures, we've studied it, is 200 to 300 years old. It doesn't have, it doesn't, but we can't observe necessarily. So our crust is that age because of tectonic activity. So that's sort of trying to figure out how active Venus is. And we'll actually come back to that idea of activity, what's under the surface, when we talk about our next planet. So if there's no more questions about Venus, I will let them come in if we need. Maybe? Okay, good. Carrying on. You can still ask them if you want. I'm going to try to find Neptune here. So Neptune is through the Earth right now, so I'm going to remove the ground. So we're staring through the ground right now because it's on the other side of the sun. So we can actually zoom in on Neptune. This is why this is fun. Do the landers last a shorter time on Mars due to the temperatures? Yes, for sure. Because they are exposed to so much pressure and temperature, the landers on Venus cannot live for a very long time. And we've not, as far as I know, we've not sent any rovers to Venus, just landers. And the difference is that landers just stay in one spot. They land, and then they do all their experiments and pictures and everything just from one spot. Rovers actually move around. So we're going to look at Neptune right now. Because we can't really see this with the naked eye, we're going to pull up all the fun information about it. Oh, cool. So the chat said that there are projects being designed for mechanical versus electronic landers for Venus because of the intense heat. Well, that's awesome. I didn't know that. That's really cool. So this is Neptune. It's a pretty cool planet. And I think it might be on the other side of it right now. Oh, nope, there it is. We're going to talk about Triton as well, which is one of Neptune's moons. And thanks for the follow. So Neptune itself was discovered in 1846. It's a cool blue planet. It's blue because its atmosphere is hydrogen and helium and methane. So methane is what makes it look blue. The sunlight hits it, reflects off, and it reflects a lot of blue light. That's not necessarily why our atmosphere looks blue here on Earth, right? This is that's because of other stuff that I don't know off the top of my head. I don't remember which chemical compositions in our atmosphere make it scatter blue to us, but this is reflecting an intense amount of blue light from the methane in the atmosphere. So the sunlight hits it, reflects off, and it reflects blue because of the methane. It also has hydrogen and helium in the atmosphere. It was discovered in 1846. It goes around the sun, so its year is 164 Earth years. And fun fact, since it was discovered in 1846, in July 2011, it celebrated its 1 Neptune year anniversary of going around the sun. So it went around the sun in 2011, once since we discovered it in 1846. Yeah, it's pretty bonkers hot on Venus. So it's actually crazy, crazy dense. It has the second largest gravity. The only larger one than that is Jupiter. Now I want to talk about what a gas giant is. Again, because I haven't done this before here, some of you might not know, which is okay. We have the rocky planets, the 4 rocky planets on the outside, the 4 gas giants on the outside of the asteroid belt, and then the Kuiper belt where Pluto lives. Pluto is a dwarf planet. It's going to be okay. I promise it's going to be okay. We could talk about Pluto another time. Or at the end of this, once I'm done talking about Neptune, because I want to make sure that we get through it. So Neptune, and we are actually going to talk about Kuiper belt objects when we talk about Triton. But Neptune is a gas giant, which means it doesn't have a rocky surface. So even though Venus looks really cloudy, it's still a rock planet, basically, because it has a rocky surface. But the gas giants, if you were to try to land on anything, you basically fall through the atmosphere, and then it would get denser and denser and denser, and then it would kind of feel like Venus, and then it would keep getting denser and denser. You're not landing on anything, but then it's like you're swimming through water, and then it's starting to crush you, and so that's what it's like trying to land in a gas giant. There's never going to be a surface to land on. You're going to reach a point where it's like, if you were to extract that, you'd be able to walk around on it. But it's not like a solid surface that we can walk around. Yeah, sounds super lovely. Space is scary. and most people remember that Saturn is not very dense because we all had those picture books of Saturn floating in a giant bathtub. But it's really cool is that aside from Jupiter, Neptune is the highest gravity because it's so dense. It is so compact together that it does have a high gravity to it, which is pretty cool. So other than that, it spins really quickly. It spins like about once every 18 hours. And it had, until I think 5 years ago, a great dark spot, which is what a lot of our pictures still have. I think this one doesn't have it. It might be on the other side. But like Jupiter's great red spot, they have what we call a great dark spot, because astronomers naming things is fun. The great dark spot on Neptune is about the size of Earth, which is really cool. And it actually has a smaller storm, which might be the one that we're seeing there, called the small dark spot. Sticking with the brand. Another cool thing about this is because of the high rotation, or not because of, it has this high rotation rate. It has these storms. It actually has really intense weather compared, especially. So Uranus is kind of its companion that, we talk about a lot. Not companion in the sense that they orbit each other, but in their similarities. But Neptune, even though it's further away, has a lot of weather patterns to it. And astronomers are always trying to figure out, why would that necessarily be the case? It rotates very quickly, so that could be part of it, that you get this high rotation rate. But because it's a gas giant, it's a chicken and the egg situation. Oh, thank you, Rose. That's so nice. You have this high rotation rate that is going to cause a lot of weather patterns. But the other thing, too, is it actually absorbs a lot of heat. So Uranus and Neptune, again, comparing each other, because they both have a lot of methane, they're both blue, they're both the two outer gas giants. Even though Neptune is much further from the sun than Uranus is, they have about the same temperature. Actually, Neptune only gets, it's 40% less light. So it gets 60% of the light that Uranus gets, right? Because the light from the sun, as you start to go further away, it's going to get dimmer and dimmer and dimmer. Then it's going to hit Uranus, and then you keep going, and it's going to keep getting dimmer. And then it's going to be 40% less bright once you get to Neptune, but they're the same temperature, which just means the composition of the atmosphere in Neptune makes it a lot hotter, which makes it more dynamic, which creates all these weather patterns. So that's kind of why we've been studying Neptune and some of the interesting stuff about it. People have been trying to figure out what kind of weather patterns you would be getting there. So that whole raining diamonds type thing, I know people have asked about before. But thinking about this idea that you do get condensation, you get snow, but snow made out of weirder stuff. And that's what's going to take us now to Triton, which is one of Neptune's moons and one of my favorite places in our solar system. So Triton is, I think, about 2,000 kilometers in radius, or in diameter. So, a decent sized moon. And it rotates opposite. So again, this is another object that is going in the opposite direction from all of the other moons. So it's behaving weird. So again, we have to think about why that would be the case. Before we break into that, one of the other coolest facts about it is one of my favorites. The planets don't give me endorsement deals. One of the other cool facts about Triton is the fact that it has geysers, and it spews nitrogen ice into its atmosphere, which then settles down as snow. So like I was talking about weather on Neptune, we get weather on Triton. It has a very thin atmosphere. It has internal dynamics that create these geysers. And then as soon as these geysers happen, it spews up, and it's nitrogen that freezes. So frozen nitrogen, very, very cold, rains back down onto the surface. The temperature on the surface is about minus 235 Celsius. Now, if you've been to science museums, sometimes you've played with frozen carbon dioxide. That's sometimes confused with frozen nitrogen, or liquid nitrogen. Liquid nitrogen. Liquid nitrogen is very, very dangerous. Chances are, if you've played with the frozen carbon dioxide, that's been the stuff that you throw into your drinks to make them smoke, or your water to make them smoke. And you would not do that with nitrogen. Dry ice. Thank you. Dry ice is frozen carbon dioxide. So dry ice is what people have normally played with, and that is not nitrogen. Liquid nitrogen we can get. That is very, very cold, very, very dangerous, but we can get it. I used to do a science show at the museum with this. You can actually, if you remove the atmosphere, condense it down into nitrogen snow. So we had a whole show about Triton, that you can make this snow. Once you remove the air pressure, it will condense down into snow, which is awesome. But Triton is actually the coldest place in our solar system, which is weird when you think about this. Okay. The reason it's the coldest place in our solar system is not because it's the furthest, because beyond Neptune, we have the Kuiper Belt, which includes Pluto. So they're even further away from the sun. So why is Triton colder? And it has to do with the fact that it's so bright. It's so bright. It's bright because it has so much of this like frozen nitrogen snow on it that it's reflecting. We call it, the astronomy term for it is albedo. It's the brightness of it, but it has a very, very high albedo. So it's reflecting a ton of light. And because of that, it doesn't absorb a lot of light, which means it doesn't warm up. So when you have a high reflectivity, a high albedo, a high reflection, it doesn't heat up at all because you're reflecting most of the light that's hitting it. So that's why it's the coldest place. Like I said, it's minus 235 Celsius, which is very, very, very cold. Now, interesting facts about that. Remember, the rotation rate is actually in the opposite direction. So this isn't the fact that it's rotating opposite, its orbital direction is opposite of the rest of the moons and everything. So for astronomers, when we see something like that, what we're thinking is that it's actually a captured object. When we see, so I talked about the formation of the solar system, right? We have this cloud of dust and gas. It all started to coalesce and clump down and spiral down because of angular momentum. It flattened out. You got the sun in the middle. You got all these planets coalescing. As they get bigger, they have higher gravity, so more stuff sticks to them, so they get bigger. And they're all in the same plane. Again, because of angular momentum, as it spins, it flattens out. You can do that experiment, maybe, if you have a ball of Jell-O and you put it on like a really fast in the middle of a very fast record player. So it's going to risk a lot of your technology, so I wouldn't necessarily do it. But if you have something that would make it spin really fast, the Jell-O will actually flatten out. So you can see that effect happen. And again, that's because of angular momentum. So you have the solar system, as it starts to flatten out, you have all these rocks that eventually become planets, and then the stuff that coalesces or gets bigger and clumps out and orbits them become the moons, but they're all in the same plane. So if you see something that's not in that plane, that's maybe orbiting a planet like this, or in a weird direction, it's most likely that it was captured after it was, after these planets and moons had all formed. So it also had formed as part of that whole system, but then because the solar system is very dynamic and stuff is getting flung around and you have all these different effects of gravity, it's pulling objects in and it gets caught. If it gets too close, it gets caught to a planet and it starts orbiting as a moon. And the phrase in here asks the great question, which is, did New Horizon make us think that Triton originated in the Kuiper Belt? The Kuiper Belt is that whole, it's like the asteroid belt, but it's beyond Neptune. Whole bunch of objects out there that are big and rocky, again, like the asteroid belt, but some of them are big enough to become spherical, like a moon or a planet. And Triton is very identical to Pluto. Now, the question about New Horizons, I don't think flew close enough to Triton to get any data because it was on its way to Pluto. And I don't think it aligned in the way that it flew close enough. I could be wrong on that. I just don't remember seeing any data specifically about Triton. But we have studied it, and Voyager flew past, and Voyager 2 flew past it. And we did get a lot of good data from Voyager 2 that we have continued to study. And that is what has kind of tipped us off to the similarity with Pluto and the likelihood that Triton was originally an object in the Kuiper Belt that got caught in Neptune's gravity and became a moon. Now, when we talk about if New Horizons, if the investigation of Pluto made us think, yeah, I do think so. That New Horizon gave us a lot more information about Pluto that tipped us off to Triton. So yeah, I mean, that's fair. Thank you for the clarification. So New Horizons was that spacecraft that flew past Pluto and took the really cool close-up pictures of it. And that information does confirm that the composition is very similar to Triton. So indeed, you can't say for sure, because we didn't observe it happen, but that is all very good evidence that Triton was originally an object in the Kuiper Belt that got captured by Neptune and is now one of its moons. So what's the difference between Triton and Pluto then? Why is one a moon and why is one a dwarf planet? I promise it's going to be okay. I do like Pluto. I like Pluto. But it's science, and we learned more. And what happens is it's science. When we learn more, we sometimes have to reclassify things because we have new data. Now, I don't want to get into it too much. I'm happy to kind of dissect it, but just to lay out the facts of what the difference is between a planet and a dwarf planet and a moon is that I know. I can when I do these live, I can feel the audience when I mention dwarf planets. It's gonna be okay. I can't do that as much here because I don't know how angry everyone is on the chat, but I promise it's gonna be okay. So Pluto. What happened is that Pluto was discovered first, again, similar to Triton, because it is a very reflective. Again, their composition is the same, so it reflects a lot of light. We discovered Pluto. Pluto's big, Pluto's round. It looks like a planet, similar to Triton. Triton is a moon because it orbits a planet. It is caught in the gravitational well of a planet. Thank you, Star Mike. And it's caught in the gravitational well of a planet, so it orbits a planet, so that's what we call a moon. Whether it's weird potato-shaped or whether it's round. If you have an object that orbits a planet, we call it a moon. There have been discussions on if we should classify moons themselves, but without getting into that, we just have objects that orbit planets, we call them moons. So that's what Triton is. Triton is one of Neptune's moons. Pluto is an object in the Kuiper Belt, and it orbits around the sun. So that's why we originally called it a planet, because it was orbiting around the sun. It did have a companion. It does have a companion that's slightly smaller, called Charon, or Charon, Charon. So Greek spelling, Charon. And this is where it breaks down, right? Because Charon, is what I'm used to calling it, sorry. Because Charon is slightly smaller than Pluto, they orbit each other. We called Charon one of Pluto's moons. Now, in 2006, I think it was 2006, thank you. So in 2006, we've been observing the Kuiper Belt. After discovering Pluto, we started to, our telescopes got better. We discovered Pluto because it was very bright, because it was highly reflective. We started to discover further objects past that. Thank you. We started to discover more objects where Pluto was, and we started to realize that where Pluto was very similar to the asteroid belt, that it was a big, flat group of stuff that was out beyond Neptune, and we called it the Kuiper Belt. Yeah, yes, I think so. Now, in 2006, we discovered another object out in the Kuiper Belt called Eris, E-R-I-S. And which is the goddess of discontent, which is appropriate, because Eris is slightly bigger than Pluto. And we have started to discover more objects in the Kuiper Belt that are bigger than Pluto. That's what kicked the whole thing off, right? We know that there's now this group of objects out beyond Neptune, but they're big. Do we call them all planets? Do we start to name every single one a new planet, and then we end up with, 2,600 maybe planets that we all have to remember their names? Or do we reclassify things because we learned things? We have, as Great Merman said, we have new info, we update our assumptions. So what they did is they said, all right, if an object is big enough to be round, so it's not asymmetrical, it doesn't look like a potato, if it's big enough to be round, orbiting the sun on its own, so not orbiting a bigger planet, but it hasn't cleared out its orbital pathway. I know Tyson gets a lot of flack for it, but I agree with him. if it wasn't big enough to gravitationally attract all the other objects in its orbital path, remember, Pluto lives in the Kuiper belt. There's a lot of other objects there. If it hasn't cleaned it up like the gravity vacuum cleaner as it's been going around, then it's not massive enough to be a planet. So that was the big kind of distinction. It's big enough to be round, to be spherical, not big enough to gravitationally attract all the objects around it. The other thing comes back to the fact that its companion, Karen, orbit, this is really hard to do like this. So you have the Pluto here, you have Charon here, and if you were to put them on a scale, that scale would fall outside of, which I forget what, this is Pluto. It would fall outside of Pluto's surface. So if you put them on a scale, which one's heavier? Again, I mentioned that Charon is slightly smaller. I can't look at the camera. Charon is slightly smaller than Pluto. So it's tipped toward Pluto, but it's outside of its surface. So they orbit, I can do it this way. They orbit a point in space outside of the surface. It's really hard. But because of that was another clarification, right? So now they're both dwarf planets, but they're a binary dwarf planet combination that they're companions, that they orbit each other. So they orbit each other around a point in space. If you took Earth and our moon and you put them on scales, the point that it would equal out is within Earth's surface. So Earth might wobble a little bit as the moon goes around it, but not enough to consider it, not nearly enough to consider them companions. You have a moon and a planet. So I hope that makes sense. So they orbit around a point where their gravity counterbalances each other. Yes, that is an appropriate way to say it. I can try to keep saying it in different ways too, if that didn't make sense. But if anyone if I confused people more, please just ask. I don't mind clarifying that at all. That's the story behind it. Obviously, we're still very attached to Pluto, but it's maybe instead you can have your favorite planet and you can have your favorite dwarf planet, and your favorite dwarf planet can be Pluto. It can be number one, because not a lot of people say that Pluto is their favorite planet. They like Pluto, but they would not only be wrong, but most people pick Saturn, so that's fine. Or Earth. Earth is a good one too. A lot of kids pick Earth as their favorite planet. So with that said, we are now up on the hour. If there are any last questions, or if anyone wants to see the night sky, I can wrap things up. I don't want to keep people too long. I know we've got kids, we've got work. It's the middle of the day for some people. It's close to dinner time for other people. So I don't want to take you too long. But if you have any questions, yeah, companions make planets wobble. That would really be good. Breathable atmosphere is important. That's usually what kids say. They're like, I like it because it keeps me alive. And that's a really good way to put it. Let me just go back. We'll go back to Venus. Oh, that's why it was all screwed up. Because I was zoomed in. So again, if people have used this before, it is really fun to use. I'm definitely going to talk about Betelgeuse next time. Betelgeuse. I think we're good. Any of the other stars here. But if you do want to check this software out, it is called Stellarium. It will automatically go right to where you are, and it will automatically pick the current time. You can fix these pop out, but you can fix them there. This is where you search for stuff. This is where you change your location and your time. And then, like I said, you can do this. If you even want to take this outside on a laptop or something, you can call it, you can put it into night mode. So it's got a red filter on it. So you can, so it doesn't ruin your night vision trying to look at the stars and look back down. But otherwise, I think this is pretty much it. I don't think we have any more questions. Again, I'll try to do this again. I'm going to do this every Friday at this time. I'll try to find another time next week. I think especially I might stream this on YouTube at a different time next week, and then here again on Friday. So more kids can join in and ask questions. So that one might be a little bit more kid focused, and we'll just focus on different planets and where we want to go. But there's a web-based version too. Cool. Thank you. But thank you everyone for coming. Thank you for hanging out, and any subscribers are welcome. I really appreciate it. I see people are now using my emotes, which makes me very, very happy. And thank you. I really, really appreciate it. Feel free to ping me with any questions that you have between now and then. This is definitely a regular thing. It's going to be on Fridays. Thank you for following. You'll get pinged. I also stream games. I also do sci-fi episode discussions where we talk about the science behind different sci-fi stuff. If you want to actually take part in deciding which episodes we talk about, that's part of my Patreon, which you can find down below. I think I missed a subscriber in there. So to whoever subscribed during this, I'm sorry it missed you. It didn't pop up for me. But thank you. I really appreciate this. Again, if you want to take part in those episode clubs, that's down below in my Patreon. And then you can find me. Most of you probably found this through Twitter, my @Dr. Erin Mack. But thank you all. Thanks for hanging out. Be safe. Try to stay happy. And, just look up. Look at the stars. It's always there for us. It's very centering. So thank you so much. I hope you all have a good time. Live long and prosper. And I'll see you the next time.